Hello everyone, my name is Brant Kudrowski, and this Organic Chemistry Lab video covers an Alkane Conformations experiment. This is part 3, modeling cyclohexanes. In this experiment, we'll use the computer program Cache to model several alkane conformations. In a previous video, I covered the modeling of butane and 2-methylbutane, and in this video, we'll cover modeling of methylcyclohexane and Tert-butylcyclohexane. The assignment involves completing worksheets by drawing in structures, reporting energies of different conformations, and then we'll calculate some equilibrium constants Keq for pairs of interconverting conformations. Features of the Cache program are covered in a previous video. You may want to check that one out if you need a refresher. I'll start off by drawing a cyclohexane by clicking on the Draw tool, selecting carbon atom. I'll left-click to draw a carbon, and then left-click and drag and release to draw additional carbons bound to it. Then at the end, I'll left-click and drag and drop onto the original carbon that I drew to make a ring. Now I'm selecting the entire structure and I'm hitting Beautify Comprehensive to add in hydrogens and fix all the bond angles. I'll move the structure to the middle of the screen. Then I'll rotate the structure to view it from a perspective where you can easily see the chair conformation. When the structure is rotated properly to see the chair, you should be able to see the axial positions pointing either straight up or straight down. Here I've highlighted the axial hydrogens in yellow. There's more steric strain associated with groups in axial positions because they're closer in space. The yellow hydrogens on the top face of the ring are close together in space, as are the yellow highlighted axial hydrogens on the lower face of the ring. The hydrogens that are unhighlighted are equatorial hydrogens. The equatorial hydrogens point in an up-down sense too, but they also lean out away from the ring. This gives them more space, and larger groups are more stable in equatorial positions because there's less steric strain. In this experiment, we're going to be placing substituents into axial and equatorial positions and observing the effect. Cache can determine the amounts of steric strain with groups of different sizes in axial and equatorial positions. We'll start off by substituting a methyl group for one of the hydrogens in the cyclohexane ring. Methyl is much larger than hydrogen, and it has more steric demand. It creates a greater amount of steric strain than a hydrogen atom. I'll start by substituting a methyl group in place of a hydrogen in an equatorial position. The easiest way to draw this in Cache is to select an equatorial hydrogen by clicking on the Select tool and then clicking on the hydrogen to highlight it. You'll notice the rest of the molecule is gray, so only that single equatorial hydrogen is highlighted. Now I'll click up in the Atom Select tool and change it from hydrogen to carbon. Now the molecule has an equatorial carbon, but it currently doesn't have any hydrogens attached, so I'll select the entire molecule by left-clicking on any open part of the screen, and then click Beautify Comprehensive to add in the missing hydrogens and optimize the bond angles. This is a nicely positioned chair cyclohexane with an equatorial methyl group. Here's question number 3 from the lab assignment. It asks you to draw the structure of equatorial methyl chair cyclohexane. Draw it in this box. Next, we'll ask the program to calculate the energy of equatorial methyl chair cyclohexane. When you get that number, it'll go in this box. I'll click the experiment menu and select New, and then I'll be prompted to save the file. I'll select Yes, and then give the file a descriptive name. I'll call this EQ for equatorial methylcyclohexane. It's also important to remember where you're saving the file. Here I'm saving it to the desktop. A dialog box appears next with a series of options. The only thing we'll adjust is the Using field. Here we'll select MM2 in place of Standard Procedure. MM2 stands for Molecular Mechanics Model 2, and it's an algorithm for calculating energies. When I hit Start, you'll notice that the molecule wiggles a little bit. This experiment optimizes geometries, bond angles, and bond lengths a little bit more thoroughly than the Beautify Comprehensive option we selected earlier. The experiment also recorded an energy for this structure and wrote it into a file in a directory that it made based on the name we gave the structure. When I search for that name, I can see a directory in the desktop labeled eq-methylcyclohexane.io. This is where our data is. The directory contains a text file called mechanics.log. When I open that by double-clicking on it, I get a report of the calculation, which includes the energy of the final structure. I'm showing that here. For this molecule, it's 6.9023 kilocalories per mole. Write this number in your lab assignment worksheet. Now we'll draw axial methylcyclohexane and repeat the process for calculating its energy. I'll start with cyclohexane and then change one of the axial protons to a carbon, select the entire molecule, and beautify it comprehensively to generate axial methylcyclohexane. You can draw this structure in the appropriate box in your lab assignment. This methyl group in the axial position is much more congested than the methyl group in the equatorial version of methylcyclohexane. The interactions between highlighted groups here are particularly bad. These are called 1,3 diaxial interactions, and with a methyl group it creates a significant amount of steric strain. We'll ask the program to calculate the energy of this structure next. We'll click Experiment, select New, and then save the file with a name that we can remember. I'll call this one AX for axial methylcyclohexane. And when Save is pressed, a dialog box comes up with experiment properties. As before, in the Using tab, we'll select MM2 to optimize the geometry of the structure and calculate an energy. Observe how the structure moves in the background when I hit the Start button. The program has made some geometry adjustments to the structure to accommodate the large methyl group. The ring is flexed slightly to get the yellow highlighted groups out of each other's way. As before, the results of this calculation are written into a text file that's in a directory with the name of the molecule. I'll find that directory and click the mechanics.log file to open up the text file and view the result. For this molecule, the final energy of the structure is 8.6836 kilocalories per mole. Record this value in your lab assignment worksheet. This is a higher energy than for the equatorial methylcyclohexane. This is due to the extra strain in the axial methylcyclohexane. Now we can start to talk about question 4 of the assignment, which deals with energy changes and equilibrium constants. With the calculations we've done so far, we can answer this part of the question that asks about delta G and KEQ for the interconversion of axial and equatorial methylcyclohexane. Delta G is the product energy minus the reactant energy, and in this equation, equatorial methylcyclohexane is written as the product and axial methylcyclohexane is the reactant. It's important to keep that straight so that you get the correct sign in your delta G value. The sign of delta G is really important. Here's a reminder of how it works. When delta G is negative, products are favored, and KEQ, the equilibrium constant, is a number greater than 1. When delta G is positive, reactants are favored, and KEQ is a number between 0 and 1. Here's another rule of thumb that can be helpful. Every 1.4 kilocalorie per mole change in delta G gives about a factor of 10 difference in the equilibrium constant KEQ. For example, suppose your delta G for a reaction was negative 1.4 kilocalories per mole. Products would be favored by a factor of 10. The equilibrium constant would be about 10. If delta G was positive 1.4 kilocalories per mole, reactants would be favored and the equilibrium constant would be 1 over 10 or 0.1. Here's another example. Suppose your delta G was equal to negative 2.8. That's 2 factors of 1.4, which equates to 2 factors of 10. The equilibrium constant would be 10 times 10, or 100. Once you know delta G for a reaction, you can calculate the equilibrium constant using this equation. KEQ is equal to E to the minus delta G divided by RT. I provided some values for T, temperature, and R, the gas constant, up here in the description. You need to use this version of the gas constant so that the units cancel out and equilibrium constant ends up being a unitless number. Now we'll move on and analyze tert-butylcyclohexane, where the tert-butyl group is equatorial in one conformation and axial in another. To draw this molecule, I'll start with equatorial methylcyclohexane and then change each of the hydrogens on the methyl group to a carbon. Then I'll select the entire molecule and click Beautify and Comprehensive to add in the hydrogens. You can draw this chair structure in your assignment worksheet in problem 3. Now we'll calculate the energy of this structure by hitting Experiment and selecting New, then giving the molecule a name. I'll call this one equatorial tert-butylcyclohexane, and when we hit Save we get a dialog box, and in the Using field we'll select MM2 and press Start. Now I'll locate the text file associated with this calculation as we did before, and we'll see that the energy of the optimized structure is 13.3768 kilocalories per mole. Now we'll go through the same process to make axial tert-butylcyclohexane by starting with axial methylcyclohexane and converting each one of the hydrogens on the methyl group to a carbon, then selecting the entire molecule and beautifying it comprehensively to give the tert-butyl group in an axial position. Draw this chair structure in your assignment in question number 3. The tert-butyl group is really huge. Here I'm indicating some 1,3 diaxial interactions that are going to be a problem for this tert-butyl group. It's very close to these hydrogens and it's going to create a tremendous amount of steric strain. Now I'll ask the program to optimize the geometry of this structure and calculate its energy by clicking Experiment, New, giving the molecule a name, clicking Save, and then getting to this dialog box where we select MM2 in the Using field. Now watch what happens to the molecule when I hit Start. The ring has become really distorted by the tert-butyl group. This conformation is going to be much higher in energy than the equatorial conformation of tert-butylcyclohexane. When we open the mechanics log file for this calculation, we'll see how much larger the energy is. The final energy of this structure is 18.8964 kilocalories per mole. That is a lot larger than the value for the equatorial conformation. Now you can complete the assignment and finish the last questions in number 4, which involve calculating delta G and Keq for the interconversion of axial and equatorial tert-butylcyclohexane. Remember that equilibrium constant is a ratio of products to reactants. Equilibrium constants that are greater than 1 and very large are indicating products are very favored. Equilibrium constants that are less than 1 are indicating reactants are favored. This is the end of the experiment. I hope it helped you understand conformations of alkanes a little bit better. If you found this video useful, check out the next one in the series or watch the prior video, and consider subscribing to my YouTube channel. My name is Brant Kudrowski. Thanks for watching.